Fourier Series explanation. Let's do a quick overview of basis vectors in finite dimensions. For a vector W in a vector space V, we can write it as a linear combination of the basis vectors. And if the basis vectors are orthonormal, we can find the coefficients using this inner product. Things get slightly more complicated when we're dealing with infinite dimensional vector spaces. All we really need to know for this video is that for the vector space R squared between minus pi and pi, we can write the functions as a linear combination of these basis vectors, and that this always holds. Even though if f of x is in the vector space R squared, it can be written like this, the reverse is not true. Given an arbitrary combination of these basis vectors, there is no guarantee that f of x will be in this vector space. This is a consequence of us working with infinite dimensions. As in the finite dimensional case, we can invoke the fact that the basis vectors are orthonormal to derive the coefficients. The inner product here is the standard used for the vector space R squared. To summarize, we can write the vector f of x as a linear combination of the given basis vectors, with coefficients determined by the inner product. This is what we call the complex Fourier series. There's actually no necessary and sufficient condition for when this will work. However, some sufficient conditions include f of x being in R squared, which should be obvious from our previous discussion. And if f of x satisfies the Dirichlet conditions, something that I won't go into here. We can use Euler's formula to write our basis vectors in this form. From this we can write our summation and coefficients like this. This is what we call the real Fourier series. And lastly, thanks for watching. Feedback is always welcome.